So in this section, we'll transition to running jobs on Perlmutter and how to do that, starting with the basics of generating job scripts and how to launch them. First, a bit about the system of Perlmutter. Perlmutter has two different kinds of nodes, the GPU nodes and the CPU nodes. The GPU nodes have two different varieties. The majority of them are GPU nodes that have 4 A100s that have 40 gigabytes of RAM per GPU, and then 256 gigabytes for the CPU. These nodes have 64 cores on the CPU side and 4 NVIDIA A100 GPUs. There are also a few nodes, 256 of them, that have 80 gigabytes of RAM. So if you need a GPU that has a larger amount of memory, then you can select these. Just to point out that in your job script, if you request that you want to run on GPUs, you may get either 40 gigabyte or 80 gigabyte GPUs, but there is a keyword that allows you to request either exclusively 40 or exclusively 80, just in case you need to use these. On the CPU side, there are 3,072 CPU nodes, and each of these has 128 processors. So these have twice as many CPU cores as the GPU nodes, but are not GPU accelerated. The CPU nodes also have 512 gigabytes of RAM, so they have more memory than GPU nodes. Finally, there are 40 login nodes, and these nodes have 128 cores since they're designed to manage many users logging on and running processes. And they also have a single GPU for testing purposes. In this slide, we have a pictorial description of what the nodes actually are like. The CPU nodes have two co-joined AMD Milan EPYC processors, each of which has 64 cores. So one EPYC processor has 64 cores, and we have a dual processor to give 128 cores on a Perlmutter CPU node. On the GPU nodes, we have a single AMD Milan core, which has 4 connections to the 4 NVIDIA A100 GPUs. And note that the A100 GPUs are all connected to each other inside of a node via the NVIDIA Link 3 connections. So some codes are able to transfer data from one GPU to another without transferring back to the CPU host. And the library that does this is called NVIDIA Collective Communications Library, or NCCL. And VASP is an example of a code that uses NCCL and can take advantage of the performance benefits of transferring data between GPUs. So this will become important a little bit later on. The other thing to discuss before looking at submitting an actual job are the Perlmutter queues, which I'll use the term queue and QoS, which stands for quality of service, interchangeably. If you look at the NERSC documentation page, you'll see that there are 12 different QoSs that you can submit jobs to, but the majority of VASP users use only 2 of these. The most important one is the regular QoS, and this has a maximum submit limit of 5,000 jobs at a time. And you can also submit jobs that run up to 48 hours in length over 24, which was a setting about a year ago. And the other thing to note about the regular QoS is it's made to handle heavy workloads. So you can use up to the entire partition, CPU or GPU partition, when running something in regular QoS. So there's no restriction on the number of nodes that you use other than the restriction of the number of nodes on the system. On the other hand, if you want to test jobs, so for instance, you're trying to debug a calculation and get an input file correct to run, the interactive QoS is a good choice for you. So this QoS allows you to go directly onto the node and then test in real time. But the number of nodes that you can use in the interactive QoS is much smaller, and you can only use it for a short time. And I have an example of the interactive QoS shortly. The other 2 queues that may be useful for VASP users are the shared and preemptive. And these have some very clever ways of allowing you to reduce the amount of charges that you're getting for your jobs. The shared QoS allows you to run jobs that use only a fraction of a node. So ordinarily, you're charged for a full node's use whenever you allocate a node. But if you run in the shared QoS, you could use 1 or 2 cores for a CPU job, for instance, or a single GPU out of the 4 GPUs for a GPU job, and then you can only be charged for the fraction of the resources that you're actually using. So if you have many small jobs, then this is an option for you. The preemptive QoS is another one that can be interesting. And this is for long jobs for which you're allowed to, you have the flexibility to interrupt them and restart them. So imagine if you had a job that was going to run for 72 hours, which is beyond the limit of the regular QoS, and you're able to checkpoint this job, then the preemptive is a good option that will let you run this and will also give you a discount after the first 2 hours of running. 2 more things to point out is, first, when you submit multiple jobs into the queue, only 2 of them are aging in priority at a time. So if you have a large number of jobs to run, then it may be useful to bundle jobs into a single job script, and have some examples to demonstrate that in slides to come. The other thing to mention is that the Perlmutter queue limits are something that have been changed numerous times throughout Perlmutter's lifetime so far. So they may be changed to suit the needs of users in the future if the user needs changed. So here we're going to demonstrate using VASP interactively. The interactive QoS is something that you can launch by using the salloc command. And the way this works is you type salloc, the number of nodes you need, declare this as an interactive job. And then in this example, I'm requesting CPU nodes for 30 minutes. And once you issue this command, you'll see these 2 lines saying that you have a job allocation granted, and then that you're waiting for resources. So after a brief pause, you'll finally see that the nodes are ready for the job. And this will be canceled after 5 minutes if the Slurm queuing system can't find any nodes for you. But normally this is a very fast and high priority way of getting on the system. If you don't get an allocation after 5 minutes, it's usually a sign of 1 or 2 things. Either Perlmutter is really, really busy at the moment, or nodes are down or are being used in a reservation. But ordinarily, you should be able to get on very quickly to test jobs using the interactive QoS. Now we turn to submitting jobs via the job scripting system, which is the way that we would normally run production calculations. So if you're new to using Slurm, the first step is to create a job script, which is a short script that has a group of statements that tell how your job is going to be run. The first group, the sbatch statements, determine control parameters that are used to allocate resources for the job. After the sbatch section, you have the section where you declare the environment, which in this particular case is just to load the VASP 5.4.4 CPU module. And then you have the command to launch your job. The -C is a shorthand for CPUs per task, which you can use either of these interchangeably. Now, the -N and -CPU parameters are the only things you actually need to declare the number of resources that you're using. So there is a bit of redundancy between the parameters that you declare in the sbat section above and then the ones that you declare in srun. So in this case, we're running a single node job using all 128 cores to run VASP 5.4.4 on a CPU node. And the -N 128-C2 is telling us to use the 128 cores spaced 2 processors apart, which I'll explain that in the next slide. If you wanted to run using 2 nodes instead of 1, then you can just double the number of nodes and then double the number of MPI processes that you are launching with. The other things to add are add the CPU bind equals cores tag, which binds the MPI task to CPUs. And then once you finished building the script, then you launch this at the command line by typing s-batch run vasp.sh, which in this case, the script's name is run vasp. And then your job script will go into the queue, and then it will wait some time and then finally run. So one thing that is typically confusing for new users that I want to spend a little bit of time on is the task binding. So if you're running a parallel code using MPI, one thing we can do is we can depict all the processes running on the node by vertical lines. And if you look closely at this, what you'll notice is that each node has a number of physical cores, which on a Perlmutter CPU node are indexed 0 through 127. But since these are AMD EPYC cores, they also have hyperthreading enabled. So each physical core actually has the ability to run two processes simultaneously on it. Now, if you have a hyperthreaded processor on your laptop, this is a very good thing to have, because it means that as you're running many different applications, such as a spreadsheet or a Zoom session or an antivirus, then they can all run at the same time and have and use a common pool of resources. But in this case, usually these tasks will stop and start frequently. Now, when you're running something in an HPC context, we have a different situation, and that is that during heavy compute loads, you'll typically be running processes that are running nonstop. And so if you want to run VASP with 256 MPI processes, you might be tempted to place all of these on each individual hyperthread using the CPUs per task equals 1 statement. And so this is not a good setting for HPC because it overcommits the CPU cores. So now what you're doing is you're running two very intense processes on the same physical core on different hyperthreads. And then the physical core has to swap back and forth between them, which decreases performance. The better setting is to always set, in this case, CPUs per task equals 2. And then this guarantees that each MPI task is given a separate physical core. And that way, each physical core is committed entirely to the one task that it's working on. And this gives the best performance. Now, if we're running VASP6 on CPU nodes, we have an additional level of parallelism to consider, and that is the OpenMP parallelism. You can run VASP6 in pure MPI mode just by setting this variable OpenMP threads equals to 1. Or you can set this to higher than 1 if you want to use OpenMP parallelism. There are advantages and disadvantages to each. The one thing that I want to point out is if you're using OpenMP threads, the issues of task binding still apply just as they do in a pure MPI case. So in this case, what you want to do is you want to change the argument of the CPUs per task parameter to be 2 times the number of OpenMP threads. And this way, when each MPI rank spawns some number of threads as determined by your OpenMP threads variable, then what you'll end up having is the threads that are spawned by an individual MPI rank will be spaced apart so that there's 1 per individual physical CPU core, as shown in this little graphic below. Finally, if you want to run on 2 nodes, the only thing that you need to change about your job script is the number of nodes above, and then also the number of MPI processes, since each MPI process automatically launches the number of threads shown here. And then you can leave the number of threads and also the CPUs per task the same in both cases. Now, if you're running on GPU nodes, there are a few additional considerations. The first thing is, because there are 4 GPUs per node, and there are 64 physical cores, which means 128 logical cores on a GPU node, you want to space your MPI ranks evenly over the node. So you always want to use 4 ranks per node and the -C32 setting, which gives you the even spacing. The other thing to mention is that because VASP is using the NVIDIA Collective Communications Library, VASP is configured only to use one-to-one mapping between the MPI ranks to GPUs. So you can't use one MPI rank talking to multiple GPUs or use multiple GPUs per a single MPI rank. So one thing you might say if you look at this is, well, I'm using 4 MPI ranks, so I'm only using 4 out of the 64 CPU cores on the chip. So that wastes 60 cores, right? But it turns out there is a way that you can make use of the additional 60 cores, and that is if you set the number of OpenMP threads to 16, then each of the 4 MPI ranks is spawning enough threads to use all of the cores on the node. It turns out that in practice, this doesn't really make a large amount of difference for most jobs. And the reason for this is that the GPUs are already handling the bulk of the computational workload. So the CPUs are not really doing a lot of work. Now, there is an amount of overhead required to spawn the OpenMP threads. And since the CPUs are not doing a lot of work, they do get some parallel benefit from doing the work they do in parallel, but it's also being somewhat balanced by the amount of overhead to create the threads. So what I recommend doing if you're running GPU jobs and you're using OpenMP threads is to try testing with 1, 2, 4, 8, 16 threads, and then just find the setting that gives the best performance for your particular job. Now, if generating a job script seems daunting for you, then NERSC has a JavaScript generator that you can use to easily generate a script, and this works for both CPU and GPU jobs. To use it, you just go to the website shown here at the top, and then you can select using the drop-down menu whether you want GPU or CPU nodes and the application and the number of processors and OpenMP threads that you want. And then at the bottom, you can click the button, the Generate Script button, and it will generate a script automatically for you. One thing to note as a caution is the setting GPU bind equals $1 is typically given from the JavaScript generator. But when running VASP, you always want to use GPU bind equals none, as this allows the GPUs to communicate with each other using the nickel library. So this is just to be aware that you want to change this setting if you use the JavaScript generator for GPU jobs. The other place you can look for sample scripts is at the VASP documentation, the NERSC VASP documentation page. And this has some very simple example scripts for both GPU and CPU nodes that are VASP specific. From here, we transition to some topics that involved a little more advanced scripting. For this particular example, due to the policy that only allows 2 jobs to age in the queue, you may want to run multiple VASP calculations into a single job. And the way you do this is by running your calculations in a loop with the ampersand, which tells Slurm that after launching to keep going on to the next iterations of the loop. And then you add this wait statement at the end, which tells your job to not terminate until all of the statements that have been submitted with ampersands have completed. In this case, what we're doing is we allocate 10 nodes, and we want to run a single VASP5 job on each node. So we run this loop, and in each iteration of the loop, we launch an S run for a single node job that uses all 128 cores. And then these jobs will all run on separate nodes in your allocation at the same time. I want to caution you about using this technique, though, in that the number of S runs that you put in your job script should be small, or ideally not more than around 10 or so. If you put too many S runs in, then Slurm has difficulty in managing these with the other things that are going on in the queue at the same time. And what will happen with too many jobs is that some jobs will either be very delayed starting, or will not run at all. The other thing to point out is if you allocate 10 nodes and run this group of jobs, if one of them fails due to a crash or if it completes early, then nodes that have jobs that are finished will just be idle, but you'll still be being charged for the nodes even though they're not actually running any useful work. To solve that, you can use several different tools. One thing is if you have a large workflow with hundreds or thousands of jobs, I recommend using a workflow tool such as Fireworks. NERSC has a number of workflow tools that we support, and Fireworks is, I think, the one that is the most popular among VASP users, as I see a lot of users use this. So I recommend Fireworks, but other tools such as GNU Parallel that NERSC supports are also good candidates if you have a workflow that requires running many jobs that you won't have throughput for. The other thing you can do is this technique of job resizing. In this case, what we've done is we want to run the same 10 jobs on 10 different nodes as we did in the previous script, but now we want to release the nodes when each job completes. To use this, what we're going to do is we're going to loop over the nodes in our node list of 10 nodes, and then we're going to launch this script, which allows us to launch a job and then release the node as soon as it completes. The one thing that you'll want to notice when doing this is you should have an idea which job is the longest running and put this job as the first one in the loop. So this is the job that runs on the head node, and this is the job that will prevent your overall job script from terminating until all of the jobs are complete. So if you have an idea which one is the longest, then you can run these and then avoid additional charges for completed jobs inside of your allocation. The last advanced scripting option that I want to touch on is an example of using the preemptive queue. The idea here is if you have a long job that you can't fit into the 40-hour limit in the regular queue, and you don't mind it being partitioned into segments, you can run this in preemptive for a reduced charge after the first 2 hours. The way this works is you start by declaring a checkpoint command, which will be issued at the end of the runtime of each segment of your job. So after the first 2 hours, the checkpoint command will be issued. And then when your job restarts, it'll run for a while, and then it will issue this checkpoint command again. Then what you declare is you declare a total job length, which can be any length that could be outrageously long, even weeks or months. This is just the total amount of time that you think your job will run. And then you also declare a couple of segments. So the segment lengths show a minimum and maximum time that your job is going to run on the queue before it's preemptive. And then what Slurm will do is it'll find a block of time in which this chunk size will fit into the queue, and then it will pick up your job and start running it, and then run until the next time that it needs to be preemptive, and then it will stop it and then requeue it for running at a later time. The other thing to mention is that because the checkpoint command is not instantaneous, you'll also want to add a minute or so to the job using these statements in order to give the job time to checkpoint whenever the preemptive signal is issued by Slurm to your job. So with this, it's possible to run a very long job at a significantly reduced cost if you are not in a hurry for getting the results. And the idea is that because you're giving Slurm the flexibility to arrange your job wherever it sees fit, you're getting a reduced charging rate for this. The final step in the running job section is there are several different commands that control Slurm and are useful for checking job and node status. So you will frequently use sbatch and salloc, but there are also commands such as sinfo, which will give you information about nodes, and then sq, which gives you information about your jobs and their status in the queue.